Uh, all right. So today I will talk a bit about Spotify and playlists at Spotify and how you can use version control to help you store a lot of data in a nice way. And playlist will be pretty much as an example. You could use this same technology for storing your own data. So that's my name, Jimmy Mardell. I'm software engineer at Spotify. I've been there for 3 years now. I'm currently working full-time on our Cassandra ecosystem, helping other teams at Spotify using Cassandra correctly. I used to work on our playlist system, which is what I will talk about today. And during that time, I learned a lot about Cassandra. So please interrupt me with a question if something is unclear. I know I have a tendency sometimes to talk a bit too fast when I'm excited about something and kind of like our playlist system, so it could happen. So Spotify, I trust most of you here know about Spotify. So it's a music streaming service, bringing you the right music for every moment. We have 24 million active users, 6 million paying subscribers. We have a lot of machines in different places in the world, and we have a lot of playlists that our users have created, 1 billion of them, more than 1 billion playlists. And so that is what I'm going to talk about today. And at Spotify, we use Cassandra quite a lot. The Cassandra cluster that stores our playlists is by far the largest cluster. So these are my 4 topics today. First, I will talk very briefly about version control in general, what it is, what you can use it for. I will exemplify this with our playlist system at Spotify, but keep in mind that everything I'm going to say is actually quite applicable for other kind of data. I will talk, then I dive into how we use Cassandra for storing our playlist, about which data model we use, and some cool stuff you can do with it. And finally, some lessons we've learned along the way. The road to where we are now has not been pain-free. We've done errors, mistakes, and so I want to share with some of them. All right, so version control. Most people really associate version control with standalone software like Subversion or Git and things like that. They work slightly differently. Some of them use a centralized server, some use more distributed, but they're really basically the same thing. Your version control files on disk. Some features of these programs is that you can create branches, you can merge branches, you can send changes back and forth, but it's quite manual process, the whole branching especially. This is not the kind of version control I'm really talking about today. What I will be talking about is rather more similar to perhaps it's embedded version control. And an example of a system using embedded version control, which I'm sure most of you have been using, is Google Docs. So Google Docs is pretty much Office in the cloud. You have a spreadsheet, you have a word processor, and more. And you can just write the documents, and you can collaboratively write documents. You can have multiple people editing the same document at the same time without things just work. You can revert, you change, you can undo stuff for a very long time anyway. And the way that works is that it really uses version control internally. It doesn't use Git or anything, but it's still version control. Everything you do are changes that just keep piling up. You don't manually branch stuff when you write the word processor, but that can pretty much happen if you two people write the same document. If you start writing, what you're really doing is that you temporarily can create small branches that are automatically merged. So this is really what we'll talk about today, embedded version control. So I already mentioned some of the advantages of using embedded version control. Another advantage could be, for instance, performance. So let's say we have a document that we want to synchronize across several devices, and this document keeps getting updated. It might actually be more performant to just synchronize the changes rather than synchronize the entire document, depending on the size of the document and the size of the changes. Another reason could be that you have business logic that depends on the history of the document. And that kind of depends on your business. And notice that when I say document here, I really mean any kind of object that mutates over time. So it could, for instance, be a shopping cart. That's a quite a short-lived object. Or it could be, as I will talk about today, playlists, which is another kind of document that mutates over time. Which brings us over to the Spotify universe. So playlists. I won't talk so much about the Spotify architecture in general, except that I will say that we are really service-oriented. We have many small services doing one thing and one thing only. We try to keep our services as separate, as decoupling from each other as possible, and independent of each other. And if a service needs just storage, well, it has its own storage. This means that we have a lot of different storage solutions. Or actually, we prefer to use Cassandra. We have Cassandra I think we have more than 30 Cassandra clusters today. The playlist clusters is, as I said, the largest one. And the playlist service in itself is also, I would say, the most complex of our backend services. And this is because we have this version control, which is, it's still not too complicated, but we try to keep things really simple as Spotify in order for us to be able to scale, while at the same time still able to add new features without risk of breaking existing features. So the playlist system that I will talk about today is called Playlist 4. And the reason for that is that all our systems at Spotify have names like the name of the systems and a version number. And most systems are at version 1 or 2. For playlist, however, we've screwed up 3 times already. Well, actually, the first 2 times were very early prototypes and were never out in the wild. So it's really the second iteration of playlist. And hopefully, we won't see a playlist 5, but you never know. So this is a playlist in Spotify. This is a screenshot from the desktop client. It's just to illustrate what a playlist really is. It's an ordered list of tracks, really. And it's important that it's ordered. It's not just a set, because the user can move around tracks, play in different order. Each track is just an ID, so we don't have to care so much about that. And playlist may contain duplicates. It has metadata, such as name of playlist and when you added a track and things like that. And so this is what you need to store in the playlist system. So what are the challenges? This doesn't sound too hard, right? So some challenges. Yeah, this is a large-scale user-generated content system. As I said, we had 1 billion playlists. It receives a lot of requests, more than 40,000 per second at peak. And some features that we wanted early on, is possibility to offline edit your playlist. That means that if you're offline, I can still modify my playlists. And when I get online again, it just syncs and everything works. If there's someone else myself or someone else has modified the same playlist while I was offline, it should still just work. We shouldn't overwrite each other. And yeah, concurrent changes is almost the same thing. In Spotify, you can have collaborative playlists, which means that multiple people can change the same playlist, just like in Google Docs. And that should just work. People should just be able to add tracks, remove tracks, move around. We shouldn't overwrite each other's changes. So how do we accomplish this? Well, you could probably do it in several ways, but we thought version control is a nice way to do it. Yeah, that's pretty much what we did. So I will talk a little bit about how this is done. So in the short answer is that every playlist at Spotify is a version control object, or you can see it as a repository of something. So we have 1 billion repositories, small repositories of objects that we keep track of the entire history. And each playlist is totally independent from each other, so we only have to focus about one playlist at the moment. So the playlists are, of course, the Spotify service stores the playlist. That's the central repository. And when the client logs in, it just fetches the latest version. It syncs its own local copy. It has a local copy of the playlist on the disk. And when you log in again, it synchronizes from the server. If you're offline, you can still have the playlist. Since it's cached locally, you can still use the playlist. But when you log in, get online again, it syncs just like you do with a standard version control. You have a git pull, for instance. Then you synchronize with what you have on the server. So that's pretty much what happens. And when you make a change to a playlist in your client, the change is immediately applied. And this allows for a really snappy UI. which is good because it feels like everything works at once. We like snappiness at Spotify. But the change is also put on a queue that gets flushed to the server as soon as you're online. And well, usually you already are online when you make the change. And this change is just added to the history, to the change graph, to the graph of changes that were made. If the service was to reject the change, well, the client has to revert and do that, but that almost never happens because the client knows pretty much what it can do and not. And this allows this automatically the client that you can make changes offline is kind of a neat feature, but it also has helped us in the past when our playlist system was feeling sad or not really working properly. Our users didn't really notice it. They could still modify the playlist as long as they didn't bring up their mobile phone and wonder why the changes didn't appear there as well. But this was when we were really saved by this like a few years ago. There were not so many mobile clients. Most people just had their desktop client and changed the playlist. So everyone was happy, even though half our servers were down. That happened. But this was many years ago. Right now, everything is very fast and working, hopefully. All right, so let's go into how we store this, how we represent a playlist on the server side. You could talk a lot about how we do this on the client side. It's actually non-trivial, some other stuff, but I will focus this talk on how we store this on the server side, since this is a Cassandra conference. I want to go into how we use Cassandra. So this is as with every version control object, you have a graph of versions. And this is an example of how it can look with playlist. And so at the bottom, we have an empty playlist that really doesn't exist. And then the user has made 3 changes to the playlist. He starts by adding 3 tracks at the first position, index 0. He then moves 1 track, and finally he deletes 1 track. To the right is the snapshot, how the playlist looked like after each operation. This is just for the convenience here. It's not really part of the graph. It's just to show you, easy to see what happens. And in the left part of this picture is the revision number. So at the bottom, we have revision number 0, and then revision number 1, comma, a hash, revision number 2, comma, hash, and so on. I will come back to later exactly what this revision number means. But essentially, every change you make receives a unique revision number. So whenever you modify a playlist, you just append to this graph. And this graph is really the only persistent storage you would need in theory. Because if you want to know how the playlist looks like, well, you can just get all the changes and replay them, and you will see the final snapshots. This might not be terribly efficient if you have a really large graph, which is why we also store 1 snapshot of the playlist, and that snapshot is usually the latest. Yes, so we're storing both the entire graph of changes and the snapshot. So one might think, okay, that seems to be wasting some storage space, right? Well, it at least doubles the amount of space, obviously, but this space is cheap today. The graph in itself is actually not much more than the snapshots, because most users just add tracks to their playlist. The majority users just add tracks. So storing all the changes for such a playlist or storing the snapshot is pretty much the same amount of space. So that's not a problem. So we have used double as much storage to be able to store both graph and snapshot. And why do we do this? Why can't we just store the snapshot only? And that is because, of course, because of concurrent edits. So concurrent changes. So you can have playlists at Spotify that are collaborative. Multiple people can change it at the same time. You can be offline and make changes, and then at the same time can actually be a very long time because you were offline. So then when you get online again, it turned out that some other had made a change to the same playlist. And so this is pretty much what happens then. The graph splits into 2 branches. As I said, with a more traditional version control software, you have to manually create a branch. Here it happens automatically. The user don't notice it. Some nomenclature here. Each of these branches, so we have 2 branches, and the latest revision on each branch is what we call a head. This is the same terminology used by Git, for instance. So when the service detects, oh shit, there are 2 heads in this playlist, I have to do something because we can't have a playlist in this split state. So what it does it automatically fixes this. So the end result becomes like this. And the algorithm used to merge this is based on operational transformation, which is something you can read about on Wikipedia. It's slightly beyond the scope of this talk, but what you're essentially doing is that you crosswise apply the changes, but modify them so they work depending on the previous change. And this is now we're getting really domain specific here. So what does that mean? If you add a track at some position, and the other branch you add a track at a different position, if you crosswise apply them, you have to modify the indexes so they end up in the correct places or so. And this can get a bit messy, but it's doable, and it's, as I said, there's research done on this topic. And but the end result is pretty nice. You get one head again, and what's even better is that the clients are completely oblivious that the playlist has branched. So the client that did the change A in the left branch, when it syncs the playlist again, it will receive change B prime, which it think happened after my change, and it will be happy. And the client that made the B change, when it syncs the playlist, it will receive change A prime and be happy. So they both end up with the same result. The clients thought it was a linear history. At the server side, we actually stored the entire branching to be able to handle these conflicts. And well, if there's a client that is even further down here, when it syncs, it will receive just one of these paths. It doesn't really matter which one. And in the client, you don't see this. You just see the end result all the time. All right. Everything clear so far? Awesome. Because now this is kind of the general things how you can do version control in software, and to avoid this overwriting dilemma, you don't need locks or anything, which is very nice. So now I'll come into Cassandra. How do you use Cassandra to represent this? So first, a brief introduction to Cassandra, how we use Cassandra at Spotify, or how we came to use Cassandra at Spotify. So this playlist system was actually the first system at Spotify where we used Cassandra. We actually used it partly to evaluate Cassandra as well, and it went well. So now we use Cassandra for a lot of things. We have, as I said, I said, more than 30 clusters using Cassandra. And we started way back in version 0.7, when a lot of features today didn't really exist, which is also why we today still not using so very many features in Cassandra. We're not using even SQL, although that will change, I assure you. There are other things we're not using, like super columns, for instance, we never tried, which I would guess was a good thing since they're almost obsolete now. All right, we're not only using Cassandra, we're also using other databases, but Cassandra is our first choice of database when we need a new storage. So, playlists, Cassandra, and data modeling. So this is a general rule. When you plan a data model in Cassandra, you really should start with the queries. And for playlist and version control system in general, there are three kinds of queries really that are the important ones. It's synchronizing your playlist. That is, you have one copy of the playlist and you want to receive the latest changes. You might also want to get a completely fresh copy of the playlist if you want to get a new playlist you haven't seen before. And of course, you might want to update the playlist. So these are sync, get, and append. I just call these different kind of queries. So we will start with the sync query. And we first need some way to represent this entire graph. So then we have a column family called playlist change, where each row is a playlist. So there's 1 billion rows in our database. The primary key is simply the URI of the playlist. That's the unique identifier. Every column is a change. So every time you make a change to a playlist, you add a new column. The name of the column is the revision number. The revision number is assigned by the server automatically. And the actual value is the change, which is just a protobuf encoded blob of the change operation, including a reference to the previous version. So you can follow the links back, so you can walk back in the graph. So you start from the head in the graph, you can just follow the links back up until the root. And some words about the version number here. So as I said, there were two parts in the version or revision number. One is a sequence number, which is simply one more than the parent revision. And then there is a hash, which could pretty much be any random hash number, just to make sure it's unique. And the reason why we have a sequence number is so that the changes are stored linearly, sequentially on disk. So when you want to you do a synchronize, you're at some revision. If you have you have a graph with 1,000 revisions, and you are at revision 990 or something, you just do a slice query at the end of the row. So then you just read the last 10 changes, which should hopefully be in the same SS table. We can't guarantee that, but at least they will be next to each other on disk within each SS table, which makes it very efficient to just synchronize your playlist. However, sequence numbers may not be unique, and this is in the case when you have branches, because then you have two changes with the same sequence number, which is why we have the hash. This is how it would look like then. On the bottom, this is the same example as I showed before, actually. So at the bottom row here, we have a short branch, which was merged at revision 4, which is the rightmost revision. And that particular revision, of course, has 2 parent pointers, since it's a bit special. All right. So this is pretty much the only kind of data you need to store to represent the entire graph. It's not enough to do everything. For instance, one thing that's kind of hard with this is to find which is the most recent revision. One might be tempted to think it's just the rightmost column, but that might not actually always be the case. Because if you have a branch, if someone modifies a playlist at a really old version because it's been offline for a long time or whatever some reason, you will actually end up with 2 heads, that one head could be anywhere in this playlist changed row. And then to find that, you would actually, in theory, need to read the entire row and figure out which change does not have any children, which is very expensive. So you can't do that, really. So instead, we use a separate column family to store only, keep track of the latest revision of each playlist. And we call this one playlist head. So it's really a subset, a very small subset of the playlist change column family. Where each row is a playlist, and each column is, again, the revision number of a head. So in almost all playlists, there is only one column, and that is the latest revision. We don't store any value in it. It's empty. This is only to be able to quickly find the latest revision. And the reason we're not using a fixed column name here, we could have, if you had a fixed column name that we kept where the value would be revision, we would, again, overwrite if there are concurrent changes. So that's why we need the revision number in the value, in the name of the column. So this is what would happen if you would, if there would be 2 concurrent changes to the same playlist. Playlist head would, for a short time, have 2 columns. And the service, when it wants to find out which is the latest revision of the playlist, it reads the entire row in playlist head, which is fast. It's just 1, sometimes 2 columns. It could be 3 if you're really unlucky. It sees that there are more than 1, and then it will start this merging operation using operational transform, and quickly change it into this. So now it's just 1 head again. It's awesome, right? So we need 2 tables, 2 column families. Playlist head is a really small column family. It fits entirely in RAM. It turns out that 95% of all the requests only needs to read from this table, which is in RAM, which is awesome. And the reason why this is quite simple is that when you log in to Spotify client, you have a lot of playlists. Most of these playlists haven't changed since the last time you logged in. We just sent to the server, I have this playlist that is at this revision, and the server says, yep, checks playlist head, yep, that is indeed the latest revision. No need to do anything more. But if it sees that, okay, I have revision 7, something of a playlist, and the latest revision is 8, then I just do a slice query on that playlist changed row from the revision I have to the end of the row, and return the data. The service will have to return the data nicely in just a single, so you don't have, if there are multiple branches, you'll have to do some business logic there to make sure. But from a Cassandra perspective, it's just a slice query at the end of the row. All right, so this is the sync query. So now I want to move on into the snapshot query, or the get query. which is, as I already said, we actually also store a snapshot, because reading the entire change row might work for a lot of playlists, but definitely not all, because we have some playlists that are updated very often, so they have a very wide playlist change row. So this is how we do that. We have a separate table column family called playlist snapshot. That one has a single fixed column name. It does not have a column name that is based on the revision. I will come back later to why. And we just store one snapshot, and of course we store which version of the snapshot, but that is part of the blob that is inside this column value. So what happens is that if a client wants the latest snapshot of a playlist, it just simply looks first in the head table again, check which is the latest version. Okay, it finds that version 9 something is the latest. Then I check the playlist snapshot value. Is that the version that we have cached? And then usually that is indeed the case, because whenever a playlist is updated, we make sure the cache is the latest one. But it can happen, for instance, in case, again, there are concurrent changes, that the snapshot might be slightly outdated. It stores one of these paths, or something goes wrong. Then the get query will actually have to update that snapshot cache. And what it does is, okay, I pick the existing snapshot, I see that it is at some old version, I'll load the relevant changes from playlist change. I might even have to go back in history. Sometimes I have to rewind the snapshot. There are cases for that. And then update it. So I can just rewind or replay changes to get from one revision of the object to another. And that is quite cool. So, but again, the majority request is simply just checking playlist head, what is the latest revision, check the cache, the persistent cache, and find it's indeed the right one. And then we just return it. And for updating playlist, that's quite simple. We still need an update. We pretty much just add it to the playlist change column family. We need to fetch a snapshot of the version the user appended it to, just to make sure that his operation is valid, so he's not trying to exceed the maximum number of items in a playlist, for instance. But in general, you just update the playlist change column family, you update the snapshot, and importantly, last, you update the playlist head column family. This is because you don't want to first update the playlist head column, because if it crashes, then you would have playlist head point to reference to a revision that does not exist in playlist change, and that is bad. But if you do it other way around, you will have a reference in playlist change that which no one will see, so that's kind of fine. So it's every request really starts by checking playlist head. So that's the one you want to update last. So this is a nice way to something that looks like you would need a transaction to make sure, but it doesn't. If you just make sure to update the tables in the correct order, it will work out fine. The data will be consistent, and everyone will be happy. And final thing about this data model is that it has some interesting when it comes to consistency levels. We use replication factor 3 on almost all our clusters. When you're reading playlist head, to make sure we really have the latest version, we use quorum, both read and write. And this is in RAM, so it's pretty fast no matter what. But for the playlist change column family, which is really big, we only need to use consistency level 1. And this is because we never mutate data. We never change data. You can never read an old value. You can do a read on something and expect a value to be there, because the playlist head said there should be a value there, and then you read nothing. But then you know that, okay, then we just retry that read using quorum, or retry on another node or whatever, but you use quorum. Because the data really should be there. So that means that the majority of the requests can be done with CL1. If a node was temporarily down or something, a few of the requests may have to fall back to quorum before we have this eventual consistency kicking in. Same thing goes with the playlist snapshot. It's just a cache. It's mostly already contained in the latest value, but the service doesn't rely on that. So we're using CL1 again to read the snapshot. If it's not the latest, but the one we want, we just update it. As long as for most requests it actually reads the latest value, which it does, it's fine. So that means that we can have a really efficient consistency level. All right, I have a few minutes left here, so I will quickly go into some lessons we learned while trying out Cassandra Spotify and particular playlist. So Cassandra is super robust. We've used it since version 0.7 for playlist. We've upgraded it all the way to Well, it's 1.1 now, but yeah, some other clusters is at 1.2. We never ever lost data. We replaced the hardware in the playlist system twice. All the machines we replaced twice. No data loss, no downtime. That's awesome. Some optimizations we've done. Level compaction wasn't when we started. We added it. Worked wonders since we have so many read requests. Compressions turned out to, yeah, it wasn't as, not from a performance perspective, it didn't help so much, even though it reduced disk usage, obviously. And that's mostly because of internal CRC checks, which the compression code used. Some other optimizations. So playlist head, we thought that one would be entirely in RAM. We trusted the Linux disk cache for this. Turned out this was not a good idea. It didn't work as well as we thought. We tried to use the row cache in Cassandra. That one is unfortunately not terribly efficiently implemented. It uses the Java heap, for instance. Just that adds a lot of overhead to things. We quickly ran out of RAM. So instead we used mlock, which fixes files in memory. And that did wonders. So we had this fantastic small bash script running on some nodes for a time, and it improved performance a lot. So what it does is it takes all the SS tables for the playlist head column family, keeps them in memory, forces it to memory, and then updates every now and then. This has since been replaced with a slightly more robust Python thingy, and it's a really good way if you have spinning disks when you really want to fix some stuff in RAM. No, it turns out now that we don't really need this anymore in our playlist system, and this is because we switched to Fusion IO disks, which helped us reduce the amount of machines in the cluster from 60 to 30 in this case, and we could have probably reduced it even more, but there are other bottlenecks that we run into now, like CPU and just memory, since we have a lot of data. Last, tombstones. I'm not sure you heard about it. I think I already heard it mentioned here several times today. And yeah, we have run into that problem quite a lot. So we noticed that even though we knew everything was fixed in RAM for playlist head, we could see that some requests, and this was repeated, we could repeat this easily, that took several seconds to read the entire row that were only supposed to contain one value. And it only contained one value from what we could see. But we investigated it a bit, and it turned out, yeah, so the problem with playlist head is, you probably realize this, but every time you make a change to a playlist, you delete one value in it and you add a new. And we don't overwrite, we actually write new column names. And so we have a lot of tombstones, but we thought, well, they should go away after a while, and we have 1 week before we compact the things, and then we have the GC time and things, but it shouldn't be too bad. Perhaps 1,000 tombstones, perhaps, that should be doable, right? Turned out we had 500,000 tombstones. Some of them are 2 years old. That was kind of bad. So we were a bit flabbergasted about that, what has happened. Why didn't it work? And this was because we didn't really fully understand how compaction and tombstones worked in Cassandra back then. So the solution we did for this, I mean, we could probably have enabled level compaction. It might help the problem, but not sure how much. But instead, we used major compaction, which is something you probably should avoid in general. But for this one, which is a fairly small column family of fits in RAM, running regular scheduling major compaction weekly is actually not that bad. It just takes, I don't remember the number, 15, 20 minutes or so to do that. And then we get rid of all the tombstones. Awesome. So those are some of the problems we've encountered and solved. We have some other problems that we have encountered and not fully solved. They are in progress of being solved. For instance, we still have this really wide row in playlist changed. We have users that automatically update playlist every 3 or 4 minutes based on music played on radio station. So we have these really large graphs that we really want to truncate. And then you have the tombstone problem again, sort of, except you can't do major compaction. So there are all kind of different things that still needs to be solved. So if you think this is interesting, just give us a call. So. Questions?
This might be an obvious question, but how do you figure out how many tombstones you've got?
Oh, we copied, yeah, no, it's not an obvious question. We copied, since it's not exposed in the API, so we copied SS tables to a local computer, and then we ran, there's a tool, SS table to JSON. Or actually, we wrote our own tool based on that, which actually just iterates through the column, just prints out the status. So we wrote some own tool, but you can use SS table to JSON, I think. I think it exposes Tombstone, so if I remember correctly.
You told you have quite a few Cassandra clusters. What were your arguments of having many Cassandra clusters versus having one huge Cassandra cluster?
Yeah. So that's all about decoupling. We want to, when we add new features to the product, we really want, we might be a bit unsure about how they will perform. So if they underperform, they shouldn't affect any other parts of Spotify. That's really our, we strive for this very, very hard. We have some of our systems that have failed because they didn't really decouple properly. So we had one cluster that stored data for two or three different systems, and then one went down, broke down, could break down other things. That was really bad. So yeah, that's the main argument.
What's the most amount of columns you have? Like, what's the largest graph you have?
As I said, we have 500,000, more than 500,000 tombstones, so it's that in that area. But I mean, those are extreme outliers, obviously. Most likely that user has very many playlists, I would guess, and then it's because we don't synchronize all playlists. We don't synchronize all playlists at once. We want to synchronize them in some orderly fashion, so we're not bashing the system when you log in. I would guess that anyway. Could be other things, but seems like that.
Given you have some very large version history graphs, are you looking at doing some garbage collection?
Yes, that's what I mentioned in the last slide, cleaning up old history, truncating it. Yes, that is something we actually do already. It's not fully automated yet because we don't have the need for that really quite yet, but yes.
You mentioned that the compaction didn't collect your tombstones on its own. Like, do you know why?
Why?
Why? The tombstones, the 500.
Yeah, so the reason it doesn't compact away, you mean? It's because the way compaction works is that you can only remove a tombstone if you compact at the same time all the SS tables that contain data for that row. So if you use size tier compaction, you usually compact 4 tables at once. If you have a piece of data that exists in 5 tables, that no tombstone in that will ever go away. Slightly simplified answer, but in general, and that is, if you start thinking about it, it all has to do with data not reappearing. So there are a lot of safety measures to make sure that data don't reappear, which makes that you can't remove the tombstones. There are ways being worked around this. This was valid a year or so ago, I think. But yes, tombstones is a problem.
But you told that you had success with the level compaction. Have you tried it on?
No, the thing is, we use level compaction on playlist change and playlist snapshot, and not playlist set. We never did that. That would indeed probably help. I'm not sure we didn't try it because we tried it immediately, major compaction, and it worked so well. We never went back and tried to do level compaction again. That would probably help, unless, I'm not sure, I'm just speculating, but if you have more than 5 levels, you will perhaps still not be able to get away the tombstone. I don't know really. It should help the problem, but I don't have any data on it.
I'm not sure if I missed it, but you said a couple of times we're using multiple databases, but we prefer Cassandra. We're using it more and more and more. Why?
Yeah, as I said, we have many systems at Spotify. Each system has its own storage solution. In most cases, we use Cassandra. So each system, playlist is one, but pretty much all the features you see in Spotify is a separate system, and each system has its own storage, its own Cassandra cluster. If it's Cassandra, it might be Postgres, it might be something else. And this is just to make sure everything is decoupled so nicely as possible. So each of our clusters really only have one key space, 1, 2, or 3 column families. So we have very small clusters when it comes to number of tables, but usually instead contain a lot of data.
But why do you prefer Cassandra more at this moment?
What?
I thought you said that you were liking Cassandra more and more.
Yeah.
Why?
Oh, yeah, because it works so well. We never lost data. All right, I think I'm out of time here, so thank you.